Yeah, so we've really only just been looking at the the system under steady state conditions so far. So what happens a long time? But actually, we're interested in what happens transiently. What happens as you set the system off? How does it progress to its steady state?
Aha, why could that be important to look at dynamic behavior rather than the sort of the unperturbed behavior? Well, the perturbation, I think, is the idea that one way, of course, of testing a model and of making more informed statements about an experimental system is to perturb it and to study the response to a certain perturbation. So, in a sense, that's what we are doing. If we look at transients, we look to the dynamic evolution following a certain artificially introduced state, which could be called a perturbation. So let's look at this and let's look at it in a way that we haven't done so far. So it's a bit of a new trick that Rob will help us understand how to do this in a simple script.
Okay, so we've been using anonymous functions all day today, and I thought it'd be nice to continue using anonymous functions in our simulation. So previously, when we simulated a function using ODE 45, we've used a separate function file, and indeed we have given you a suitable function file to attempt simulation with in the materials.
Yes, you can download a suitable function for a use that we have introduced before when the model is in a separate function file. So if you remember how that was done, I think we used the toggle switch. We ran the toggle switch, and then you can do it, of course, in the same way, but we'll have a new way of doing the same thing today.
But instead of using a function file, a function in a file, we can also use an anonymous function in the ODE 45 function. So we just need to be careful of a few things. So we had defined a function previously up here. So I'm going to take that as our base. So remember, this was the anonymous function that had the feedback inhibition and the rest of the Goodwin model. Okay, so I'm just going to copy that and paste that down here. But ODE 45 expects a couple of things. It expects a time variable, and it needs to return x. And x needs to be a column vector, whereas previously we've been using a row vector. So that's the easiest change to do. First thing, we just need to change this comma to a semicolon.
From row to column, yes.
I'm going to just make this move on to 2 lines. So I just use a ... to say to MATLAB, this is the same thing on another line.
To continue making it easier to see.
And the other thing we need to do, it needs to return t and then x. So we just need to change x to t, comma x.
Right, so let's get this straight. So what we are doing now, we want to use this in ODE 45, and this is imposed on us by the convention in which ODE 45 works. For no other reason. That's the reason why we have t comma x. We want to have the time, numerically the time vector, and we want to have both variables captured in the x vector.
This is one other thing I'd like to do, and this isn't necessarily important, but I would like to change this predefined feedback inhibition function to the most general form. So actually I'm just going to copy this form of the equation. So remember, we defined it first with all the parameters, and then we made specific summary functions for use in fplot. But actually I just want to use the full version in our file so we can change the parameters more easily later. So I'm going to change our feedback inhibition 2 just to call feedback inhibition. And the only other thing we need to do is we need to change our x here to call the right variable, so x2. Okay?
Right, because we have these two variables x1 and x2. So that's two variables captured in this x now, and the feedback is done or executed by the second reactant. And we have specified all our four constants, and we're looking at a linear impact in inhibition by the exponent 1, which is the last number of that 4.
I thought I'd use this version because I just like having all of the material in the same format in the same file. So I'm just going to copy and paste this line down below. I'll probably comment it out, but just to show you what feedback inhibition looked like originally.
That's where it comes from.
Yeah. So this function, which we defined up the top of the page, is just being used here.
Right, so f now captures our whole model.
Yes.
And it has two variables, namely the time, sort of the independent variable, and the dependent x, but that is composed of two variables in itself. So because we have two reactants, and if we had a model with 10 reactants, then x would capture all 10 of them.
Yeah.
And we could refer to them as x1 through x10, similar to what we do here.
Okay. So we just need to simulate now.
Now to simulate.
So we know that it outputs a t vector and an x vector. So a time vector and then a vector of the concentrations corresponding to x1 and x2. Using the ODE45 function, we need to pass it the function we've just defined, f. The limits, the start and end points, the time span, and then the initial conditions. Should we say 0.1, 0.1?
For example, yeah, doesn't really matter. You can also, what would you do if I asked you to do random initial conditions?
Well, we'd need to find a function that did random numbers.
Aha.
Which you'll have to remind me in MATLAB.
Rand.
Is it just rand?
R-A-N-D.
And then 2 to give a two element vector? Oh, that's
a 2 by 2 matrix, so you
So
have to specify 2, 1.
Okay.
Gives you 1 column, 2 values, and 1, 2 gives you 2 columns in 1 row.
Okay.
So that's the way of generating. But I think we're fine just taking 0.1, 0.1 as an initial state, so say 2 small concentrations. It's arbitrary, right? We have to remember that this is what we said. And
okay, and then I guess we just plot the output. So plot t comma x. Okay.
Right, so that would be all. In a sense, we have our model defined as a function f, and then we use f in ODE45, specify what is needed, namely the period of time we want to simulate, and give 2 initial conditions. So it's actually a very compact way of writing it, and those more experienced with programming in MATLAB know that many things can be written in a very compact and dense format once you reduce it to what is really needed.
I just like this way of producing functions in anonymous functions rather than function files if the function is actually quite small and can be written quite neatly. Of course, if you need more complicated logic, if you need to do if loops, if functions and loops and similar inside your function, then this isn't appropriate. You should do a function file.
Yes, definitely. If you have a large-scale model where you want to be aware of which variable is which reactant, then you wouldn't use x1 and x2. You would actually write the explicit equations to be able to look at individual contributions that you are interested in.
Okay, should we run this? Okay.
So what do we see here? Can you remind me what the situation was with respect to the feedback?
We did have feedback in this value.
So we do have feedback. What's our n value?
Our n is 1.
N is equal to 1.
And the constant of inhibition is 0.1.
And we have a constant of inhibition. So we see the case where there's the inhibition where x2 is linearly, so it's not in the quadratic form, it's x linearly, but it's already inhibiting. So I would actually be interested, what does the model look like when it's not inhibiting at all, when there's no feedback at all?
Okay, let's just change
possible?
ki to 0. And then if we can run this in the same. Okay, we'll just run this and then just make the lines thicker. So they go up to a steady state. So they start off small, and they just increase up to the steady state where they're both equal to 10.
Right, so what we have here is an outcome of the simulation of the linear pathway, namely a reaction that produces X1 that leads to the production of X2 and the decomposition of X2. And this linear pathway actually has a steady state at 10, a number that we remember when there's no inhibition at all. So both variables starting at these low values attempt to reach this steady state, and they do succeed within this limit of 10, whatever then time units are, within 10 model time units. And the only difference that we see is that x1, our first variable, takes the lead, of course, because it's the first part in the chain. So it first receives input via the constant input flux, which is modeled by A. And once this rises, it can then lead to the synthesis of the second reactant, which is the red curve, which sort of follows with a bit of a delay, but eventually reaches the same final value. Can you now put the inhibited case on that same graph? Is it possible to rerun the simulation with inhibition? Yes, with hold on, so that we can see how the relative sizes of the rises and steady states are in the two cases.
So just set Ki back to 0.1.
Back to 0.1 means a finite inhibitory constant or inhibition control tells us that we will now have the case where X2 actually impacts negatively or in a way that reduces the rate on the first term, and we can actually see what inhibition means. In this case, it means that steady state values get much lower. In this case, this comparatively small thing of 0.1 was already enough to reduce our value to about a third, is even less than a third of the original value.
So this is the orange and the yellow and purple lines. But it's interesting, they look like they start in approximately the same sort of rates. So down here, just as they're starting, actually the system seems relatively similar with the inhibition. I suppose because there's not much of the X2.
Yes, that is understandable. In the limit of very small concentrations, of course, they will be the same. Right? If we go to 0, then initially they will start the same because the 0 value of X2 will have no inhibitory impact. So we'll just start in the same in both cases. But once X2 starts to grow, so that red curve here, once it starts to go as a purple curve, it's because it impacts negatively and it leads to this maximum in the response of the first. And we can see we have this hump or bump or whatever, it goes up and then comes down again to the final steady state value. And you can imagine that if we make this Ki even larger, that this effect will be more pronounced, leading to even lower steady state values in both variables.
Should we see what happens when we change n?
Now we could take a look at the inhibition now if it's quadratic, where we know this impact of the negative feedback is less for small concentrations of X2, but is larger for large concentrations of X2. If I just run it, maybe we'll make this a little nicer, probably taking the big two curves from uninhibited away altogether. Yes, and we have it nicely zoomed in.
So this is now the green and the blue curves that we're interested in. So it seems to, well, it's a lower steady state, as we already knew. Actually, the dynamics seem to be a little bit faster. So the hill starts sooner.
It's previously,
and then the valley, well, actually, it may be about, so it looks like it's a little bit, reaches a minimum a little bit earlier.
It is, yes, it is. So we get with the quadratic inhibition, we get a faster response, so to speak. We get a faster rise, slightly faster, but we can see also a steeper decline. And in general, also the final steady state lower, so means stronger inhibition. And we can see, of course, we are at values for both concentrations which are above 1, so we expect the quadratic term to win over the linear term.
I guess then that makes me want to ask the question, what happens when we have an even stronger, rather than quadratic, maybe to the power of 5, 10?
Yes, why don't we try it?
Try 10?
And this is just as a comment here, this is of course what you would then actually do when you do research. And you then start thinking about this, and you make numerical experiments to find out what other properties does this model have. So let's look at this.
Okay, so I'm just going to remove
It's a
the
curious
n
thing.
equals
Now you
2.
have to remove the previous one so we can have a bit of a comparison. Could you just only show the first variable in both cases rather than the second? So that's the first variable, the response of the first variable, or the transient of the first variable in the case quadratic feedback inhibition. This orange.
Linear is in the yellow, orange.
Is it not quadratic?
I can show quadratic as well, which is in the green.
Ah, that was the green. Okay, so the linear. Oh, let's take all three. The linear is the orange. Quadratic is the green. And finally, the power of what was it?
10.
10 is the red curve that goes to even lower levels, but curiously shows sort of a damped oscillatory response. Which is an important feature to notice. It means that depending on how the function looks like, or what the function looks like, means we can even have qualitatively different responses.
Yes.
You can read all of this theory behind this in the Goodwin book. It's all very well explained. And one thing that we maybe don't want to do now, but one thing that's known from control engineering is that negative feedback of this form, and it's nonlinear, is of course also capable of making this whole thing unstable and bringing the system to oscillate over time.
Sustained oscillations.
Sustained oscillations. And in a way that is not quite unlike the strong whistle that you can create by a microphone if you turn it towards the speaker. An instability that goes with a constant frequency. And this is a well-known feature of many feedback inhibition loops. And in particular, it's been found in many experimental recordings of signaling cascades when you give a strong signal to a membrane-bound receptor. That downstream molecules actually respond with something that looks like damped oscillation, and people have wondered what that means. And it often points to the fact that there is negative feedback inhibition loops in that signaling cascade. So the cascade is not a one-way, but there's actually a network having feedback loops.
Okay.
Yes. So we can close this down. We are finished with our exercises. And as a